significance of the speed of light being constant in all inertial frames of reference and how this lead to the concept of time dilation?
Okay, so essentially, this is a very good question. So the speed of light being constant in all reference frames, of course, comes from the four Maxwell equations. And why is it significant? That's an absolutely wonderful question. So normally, you already know, obviously, since you're in your third year post-grad, that if we just have a regular Euclidean point in space, so what is the only thing that is invariant in R3, no matter what reference frame you're in? The only thing that's invariant is distance. Velocity can change, acceleration can change, position can change. But the only thing that doesn't change is distance, no matter if you rotate your reference frame or you translate your reference frame. So distance is invariant in R3. But the thing is, this changes when you introduce the fact that the speed of light has to be constant. Now, instead of our constant being something like this, like dl squared is equal to dx squared plus dy squared plus dz squared, instead of this being our space-time interval, now, to keep the speed of light constant, we have to add an additional component. And, of course, this is what leads to time dilation. Now, I'll give a Neil deGrasse Tyson way of explaining time dilation, and I'll give an actual mathematical way of explaining time dilation. So, of course, the fact that the speed of light is constant in all reference frames, the velocity, or speed, just is equal to the distance covered over time. But distance is invariant, but distance is invariant, and it seemingly so is time in Newtonian. So a velocity is supposed to change to accommodate all reference. Okay, I'm going to explain it a little bit better. So let's say you're in a car traveling at 30 kilometers per hour. I don't know what you guys use over here. And then somebody is walking by at 3 kilometers per hour. So then, and let's say you guys are walking in the same direction. Then, in the car, you will perceive yourself as traveling at 0 kph, and that guy is traveling backwards, 27 kph. And I know you might think that sounds like nonsense, but I mean, look on the outside of your car or your bus or wherever you, whatever you use to get here. I mean, if you see any still objects, you will perceive them as moving backwards away from your direction of motion. So, however, this is not the case with light. If you have a guy running over here at 3 kph, totally fine. But now, let's say we have light. Light is going to be moving here at 3 times 10 to the 8 meters per second. Now, converting that into kilometers per hour, first we have 3 times 10 to the 5 kilometers per second, and then all we have to do is convert this, multiply this by 3,600, so that we get hours, and then all we get is 10,800 times 10 to the 5, or 1.08 times 10 to the 9 kph. So it's safe to say this guy is outspeeding you by a little bit. But the fact of the matter is, no matter if you're traveling at 30 kph, or 300, or 3,000, or 30,000, no matter what, you'll see this ray of light is traveling at the exact same rate. But this conflicts with our definition of velocity. Velocity is supposed to be relative. So in order for that to change, distance has to be variable and time has to be variable, which is exactly the concept of Lorentz transformations. And normal transformations in Euclidean space, the distance between two objects is held constant. Obviously, this is just the Pythagorean formula. But here, it's not the distance that is being held constant. This is what we call the space-time interval. So, essentially, transformations in relativistic space are supposed to make this stay constant. And so, Transformations that keep this constant are known as Lorentz transformations. And long story short, you can essentially calculate what these Lorentz transformations are, their general form, and what it will give you is a proportionality constant, gamma, times whatever vector you originally had. Okay, well, let me write this in a better way. The Lorentz transform is often written as a capital lambda. So what will happen is you'll often have capital lambda times any vector you have is going to be equal to the same exact vector times a certain constant called gamma. And this constant, which you can calculate, is specifically equal to 1 over 1 minus v squared over c squared. And this is essentially how you calculate time dilation. So, as far, what I believe is that the time that others observe is going to be the time in your reference frame, also known as the proper time, divided by gamma. So essentially, time dilation occurs because the velocity of light has to stay constant in all reference frames, but this contradicts our normal sense of velocity in Newtonian mechanics. So to change velocity, which now has to be invariant, to keep velocity the same, we now have to change distance and time, which were originally invariant. And so this results in length contraction and time dilation. So essentially, the fact that the speed of light has to be the same in all reference frames results in all other physical quantities being stretched and squeezed by some certain Lorentz transform to account for the fact that the speed of light has to be the same. So that's the significance of the speed of light being constant. Thank you. Okay. There we go. That's fine.
Right hand.
Oh, got it. Okay. Take your question now. Great.